Newton's third law. Everybody's heard the phrase, for every action there's an equal and opposite reaction. That's one version of Newton's third law, but not a very good one. Action is kind of a vague term. Much better to say, for every force there is an equal and opposite force. That is, every force, according to Newton's third law, every force in the universe has a partner. Every force comes along with a second force, an equal and opposite force. And we need to stop and think about what equal and opposite mean. Equal really means two things. That one of them is kind of obvious and the other one isn't. The obvious part of equal is that they have the two forces in that Newton's third law pair will have the same magnitude, the same strength. The other part of equal that is not quite so obvious is that they are the same type of force. For example, my hand pushes on the blackboard. So the push from my hand is a normal force. So my hand is a vertical surface and it's pushing horizontally. A push that's horizontal to the surface it comes from is a normal force. But of course, when I'm pushing, I feel resistance from the blackboard. That's because the third law partner of my push is a push back from the blackboard on me. But of course, that push from the blackboard is a horizontal push coming from a vertical surface. In other words, it's another normal force. I'm applying a normal force to the blackboard, and the equal and opposite third law partner to my force is another normal force. The two forces in a third law pair are the same type of force. And I can also feel the equal magnitude part. If I push harder, I feel more resistance from the blackboard. In other words, if I push harder on the blackboard is pushing harder back on me. So equal and opposite. Equal means two things. Opposite also means two things, one of which is obvious and the other one isn't, but very important. The obvious part of opposite means the two forces point in opposite directions. The force from me on the blackboard is pushing that way, and the force from the blackboard on me is pushing in exactly the opposite direction. Opposite also means that the roles of source and the thing that's feeling the force are flipped when you go from looking at one force to looking at the other force. So one force in this Newton's third law pair is a push from me on the blackboard. The other force is a push from the blackboard on me. That's always the pattern in whenever we're talking about a force and its equal and opposite Newton's third law partner. A force from one thing on a second thing, and the third law partner force is a force from the second thing back on the first thing. That's an important pattern to look out for, and if you're able to recognize that pattern when it appears, a lot of other things will become easier for you. Let's look at an example of this. Imagine that I'm pushing a box across the floor, call it box A, and then in front of box A there's another box, B, that's about box that's also getting pushed across the floor? Well, let's draw force diagrams for each of these three things: box B, box A, and me. First, a force diagram for box B. But in this force diagram, we're going to do something that we haven't done before. For each force, we're going to think specifically about where it came from and what it's acting on, because that's an important thing to keep track of when we're dealing with Newton's third law. So what are the forces on B? Well, of course, there's the weight of B, which is just a gravitational force from the Earth on B. So I can just write, instead of writing it as weight, I'll just write it as gravitational force from Earth on B. And then, of course, B isn't falling. The floor is supporting B. That means there's a normal force from the floor on B pushing up and canceling out any effect from this force. Normal force from the floor on B. And then what else is there? Well, B is being pushed forward. It's important to recognize that B is not being pushed forward by me, because I'm not in contact with box B. These pushes, they're going to be normal forces, are, like I've said before, contact forces. That is the only thing that can, other than the Earth, the only thing that can apply a force to box B is something that's actually in contact with box B. Right? The floor can't push up on box B with a normal force unless the floor is in contact with B. Similarly, it's A that's pushing B to the right. And of course, that's a normal force, because this surface of A is the surface that's pushing on B. It's a vertical surface, and it's making a horizontal push. Another push that's perpendicular to the surface, so it's another normal force. And then sliding, it's sliding, and when there is sliding, unless it's an extremely smooth surface, whenever there is sliding, there is kinetic friction, always opposing the motion. And of course, kinetic friction is a force from the floor on B. Okay, now how about box A? Just like for B, there's the weight, the gravitational force from the Earth on box A. And just like for box B, there's a normal force canceling out the effect of the gravitational force, a normal force from the floor on box A. And then, of course, there's me. I'm over on this side pushing on box A. The push comes from my hands, which are vertical surfaces, and then the push is horizontal. So that's another normal force. A vertical surface, my hands pushing horizontally on A. So normal force from me on box A. And then this is also sliding. So sliding this way. So again, there's kinetic friction pointing backwards, pointing opposite to the velocity, kinetic friction from the floor on box A. But there's still one more force. There's still one more force. Go back to B. Think about where this force came from. A normal force with which A pushes on B. Remember where normal forces come from. They come from the elasticity of these surfaces. This force happens because B was pushing backwards on A. Right? When A tries to push forward, it feels a little bit of backwards resistance from B. B is pushing to the left on A, and that makes this part here where B and A are in contact, it makes the molecules of A squeeze together a little bit more than they would normally, and because of the elasticity of solid material, those molecules want to stretch back to their original bigger separation, and in trying to stretch back, they'll push to the right on B. This force comes about, in other words, because this side of A was first being squeezed, pushed by B. Normal force from B on A. I'm going to rewrite that because there's a lot of stuff crammed into a small space there. So A, there's the normal force from the floor on A. There's a gravitational force from the earth on A. There's a normal force from me on A. There's friction, kinetic friction from the floor on A. And there's also a normal force from B on A. Okay, so those are the forces on B, forces on A. Now how about the forces on me? There is, of course, the gravitational force from the earth on me. And normal force from the floor on me keeps me from falling due to this force. And just like the interaction between A and B, because there's a push from my hand on block A, that force came about because A was in fact pushing backwards on my hand. When I push on A, I feel some resistance from A. A is pushing back on me, and in fact, as A pushes back on me, right, the molecules here in this part of my hand get squeezed, and they want to expand back to their normal separation, and in doing so, they push on A, and that's the source of the normal force from me on A. But of course, we got that force in the first place because A was pushing to the left on me and squeezing the molecules in my hand. Normal force from A on me. And then there's one more force. I'm walking normally, which means as I take a step and push off of my rear foot, my foot does not slide backwards. My foot stays stuck, my foot stays in contact with the floor. So there's some sliding that could have taken place, but it's being prevented. Whenever sliding could have taken place but it's prevented, it's because there's some kind of friction force to prevent the sliding. And the kind of friction force that prevents sliding and keeps things stuck in the same place is the force that we call kinetic friction. Or, sorry, not static friction. Static friction. Static as in not changing, not moving. It keeps my foot from sliding this way, so a force that prevents sliding this way always points opposite to the slide. So the static friction force on my foot points that way. Static friction from the floor on me. Now, among all of these forces, there are some third law pairs. And here they are. Here's one of them. The normal force from B on A and the normal force from A on B, they are a third law pair. They have all the characteristics of a third law pair. They're the same type, they're both normal forces, and they're pointing in opposite directions, and the role of the source and the receiver of the force are flipped around when you go from one force to the other. Here's a force from A on B, and the third law partner is a force from B on A. One force from one thing on a second thing, and then a partner force from the second thing back on the first thing. That's the pattern for a third law pair. Another third law pair is these forces. A normal force from A on me and a normal force from me on A. They fit the pattern again. They're the same type of force, and they're in opposite directions. This one's to the left, this one's to the right. And again, here's a force from me on A, and then that flips around when you look at the other force. A force from A pushing back on me. I push on A pushes back on me. That's how the third law partner forces work. One important thing to notice in this third law pair, there's a force on A and a force on B. The two forces in the third law pair are on two different things. That's always the way it works. The third law partner forces always involve an interaction between two things, between thing A and thing B in this case. And here, this is a force on me, and its third law partner is a force on A. So again, the two forces in a third law pair are on two different things, and they're describing an interaction between those two things. One is a force on me, one is a force on A. Even though there are lots and lots of other forces in this situation, those are the only third law pairs. Every one of those forces has its own third law partner, but these are the only cases where both forces in the third law pair are actually present. Let's look at one more example. What, for example, is the third law partner force to this thing, the kinetic friction from the floor on A? Let's look at that in a little detail. So the force that we're thinking about is a kinetic friction force from the floor on box A. How about its partner force? Well, the partner force is equal and opposite. And we know that equal means they're the same strength, and equal also means they're the same type of force, which means the partner force must also be kinetic friction. And where this force from the floor on B was pointing to the left because B was moving to the right, the partner force has to be in the opposite direction. And then this was a force from the floor on A. The role of source and receiver of the force are flipped around when you look now at the partner force. So this must be a force from A on the floor. That seems a little weird. How can we make some sense out of this? Well, imagine that you're a little bug sitting on B. From your point of view, you're just sitting still as box B moves this way. From your point of view, you're just sitting still, and everything else is moving this way. In particular, from the point of view of those of us who are not sitting on box B, we see box B sliding this way, sliding to the right across a stationary floor. But from the bug's point of view, the bug feels stationary and sees the floor sliding to the left underneath box B. So the bug sees something sliding, the floor, and it's sliding against another surface, the bottom of B, and so the sliding thing is going to feel a kinetic friction force from the thing that it is sliding against. The floor is sliding across the bottom of box B, so box B must be applying a sliding friction force on the floor, a kinetic friction force on the floor. And from the bug's point of view, the floor is sliding this way, so any kinetic friction or sliding friction force on the floor would always point opposite to the direction of velocity. From the bug's point of view, the floor's velocity is this way. So from the bug's point of view, there has to be a kinetic friction force the other way. And that's the force here. The bug sees the floor sliding across box A, and so the bug will realize that A must be applying a sliding friction force or kinetic friction force to the floor. Whether that might seem strange at first, but really think about it. Whether you look at things from a perspective of somebody standing over to the side and watching me push the boxes, or whether you think of things from the bug's perspective, sitting there on box A, both perspectives are equally legitimate for trying to describe this situation. So it's equally legitimate, equally true to say that there's a friction force on A from the floor because A is sliding across the floor, and then it's equally legitimate to say there's a kinetic friction force on the floor because the floor is sliding across the bottom of box A. That's another example of a third law pair. When you think of third law pairs, you think of some kind of strange pairs sometimes. This is kind of a strange pair. At least it seems strange at first. The more you think about this stuff, you'll get used to it. But yeah, right now it seems a little bit unusual that there would be such a kinetic friction force. One last example. Let's take the gravitational force from the Earth on me. The gravitational force from the Earth on me is pulling down on me. The partner force has to be another gravitational force from another gravitational force, because a force and its equal and opposite force, a force and its third law partner, are always the same type of force. Both forces in a third law pair are always the same type of force. So it's a gravitational force again, and it has to point in the opposite direction. So it's pointing up, and now again the roles of the source and the receiver are flipped around. This is a force from me pulling on the Earth. Anything with mass feels a gravitational force, and the Earth has mass, so it's certainly going to feel a gravitational force. Thing is, anything that has mass will also apply gravitational forces to any other mass. I have mass, so that means there's going to be a gravitational force from me pulling on any other thing that has mass, like, for example, the Earth. The strange thing about this third law pair is that since they are a third law pair, the forces have to be equal magnitude, equal strength. And that seems strange that the Earth would be pulling on me just as strongly as I pull on the Earth. Strange, but it's true. It makes sense, however, if we think about Newton's second law for just a minute. There's some acceleration because due to the gravitational force on me. So the acceleration on me is just the result of the force from the Earth on me. Gravitational force divided by the mass of me, and then force from me on the Earth. It's a force, so it could cause an acceleration. So force on the Earth is just the gravitational force from me on the Earth, which is just as strong as this. The gravitational force on me and the gravitational force on the Earth are a third law pair, so they're equally strong. So I'll just use the same variable name for both of them, plain old Fg, and that's divided by the mass of the Earth. Well, compare these quotients here. They both got equal numerators because the forces are equal, because that's what Newton's third law says they have to be. But this denominator here is millions and millions and millions of times bigger than this denominator, which makes this fraction millions and millions and millions of times smaller than this fraction. So the acceleration that the Earth gets is millions and millions and millions of times smaller than any acceleration that I would feel. If I'm up on the top of a ladder and jump down, you can notice that I accelerate. It's easy to notice that I accelerate because I get a pretty large acceleration because my mass is relatively small. The Earth is accelerating too, but you don't see it because this factor is huge, huge, huge compared to this. So this quotient and therefore this acceleration are tiny, tiny, tiny compared to this acceleration.